Hello everyone. We are going to be talking about Google Dremel today, and that is a paper from 2008. Dremel has been an extremely influential system. In fact, even now, which is more than 15 years later, you will see that Dremel is being used at Google by a system called BigQuery. It's been so influential that VLDB awarded it the Test of Time Award in 2020, 12 years after it was published. As a software engineer, it makes a lot of sense to know about this paper. Now, the first thing is, what is Dremel? In 2008, Google had a lot of data, petabytes worth of data, which it wanted to analyze. They wanted to mine the data, and product managers, engineers, CXOs wanted to write queries on this data to see what patterns they can use. Now, the problem here was that petabytes worth of data takes a lot of time to scan, a lot of time to process, and a lot of time to output. Usually, product managers and CXOs want to fire one-off queries. For example, a product manager at Google may want to see how many people who take long rides, let's say Mumbai to Goa, stop over at restaurants for food. So based on this information, maybe you want to serve contextual ads. We know you're on a long drive, maybe we can give you an ad for a restaurant which is on the way. This is just an idea. You're kind of brainstorming right now. You want to know the data first to help you make a decision. But how do you query this data? 2008, the standard way of doing things was MapReduce, which basically meant that you would have jobs running, and these jobs were defined using code. Engineers would write this code, write these scripts based on what they heard from product managers. And once these scripts executed, you would get an output. In our example, that would be the number of people who go to restaurants nearby during a long drive is 56%. The product manager looks at this and says, this is great. I want to now know, in the last 3 months, what's the percentage? And before that, what was the percentage? So is it that this number is increasing? Are people more prone to taking a restaurant nearby during a long drive? What do you have to do now? You have to write another job. You have to write code again. Basically, this product manager has to go to a software engineer, explain to them what the task is, wait for them to write the code, wait for them to execute the code. After the execution, based on what you see, based on the insight, you might ask a new question. The iteration time for this was very large. This used to be in days. Okay, and if you would have dedicated engineers just for MapReduce jobs, it would still take hours, usually 1 to 3 days, before you could make any sensible decisions. That's a long time. CXOs had the same problem. Now put yourself in the principal engineer's shoes. 2008 Google, you have a lot of product managers complaining about engineers being slow or complaining about the systems being slow. Sometimes this MapReduce job fails, you have to restart it. It's a nightmare. And you have engineers complaining about their time being wasted by product managers because half the day is spent just mining data and the rest of it is spent talking to PMs, understanding their requirements. Google decided that they need some sort of interactive analytics system. Interactive meaning you want to get results for any query within a minute. The second thing you want to do is free up the software engineers who are currently just writing MapReduce jobs. You can utilize them by putting them in different teams, and you can provide an interface to the product managers such that they can query the data themselves. This will remove one layer of dependency. The software engineers no longer need to be consulted before any kind of query is fired. So you want to remove the SE dependency. How do you do this? One way would be to give an extremely detailed interactive analytics tool where a product manager without any coding experience can easily fire queries. What kind of tool will that be? Most product managers know SQL at a high level at least. And if they don't, they can hire a data analyst. They can use a team of data analysts who are great at writing SQL queries. Okay, so this is much cheaper. You don't need to have software engineers writing MapReduce jobs. You can have data analysts do this. or you can have the PMs themselves writing the SQL queries. This was one major decision which has really helped Dremel become very popular in the analytics space. And for interactive analytics, answering queries very quickly within 1 minute, you can't do this without looking at the access patterns of the system. How is this system being used? So usually the system is used for getting count queries, statistical queries. This is a great insight. CXOs normally don't want to get the rows. I mean, the people who actually went to a restaurant, that doesn't matter to them. They want the count, aggregate, percentage, stuff like this that helps them make decisions. So you're mainly looking for statistical data when it comes to queries. And usually this data is distributed across systems. So you need to filter through these systems and then aggregate the data. So these two parts, filtration and aggregation, have to be extremely fast. You want answers within 1 minute. Filtration and aggregation have to happen blazingly fast. Let's understand how this happens. So this is the query architecture of Dremel. You see that you have clients who are product managers using a dashboard or using some sort of interactive user interface. They fire a query which goes to the query manager. Okay, the query manager is part rate limiter, part load balancer. It finds which shard should be hit based on how much load is there on each shard. If you don't know about sharding, please check out the video. It has a double role, right? So you have a query manager which is sending queries to the root. And the root node, as you can expect, is the root of a tree. So this is going to aggregate all the results and is going to return a response when the query has finished processing. What the root does is it looks at the query, looks at the shards which have to be hit for this query. So each shard manages a range, a key range, let's say K1 to K1000 here, and you have K greater than 1000 managed here. If you want keys 100 and 1100, then the query has to flow to both nodes, both shards. What are these shards? Are these logical entities? No, they are physical servers. This shard then recursively internally again queries its subshards. So you get the query of 100 here. Maybe the first 500 exist here and the next 500 exist here. Because 100 is less than 500, you don't need to query this shard. So that's some saving. And so K100 will eventually reach the leaf node where it belongs, and the leaf can pick it up from its local disk if it has it. If not, it will go and pick it up from a distributed file store. In 2008, that was Google File System, GFS. You might have heard of this. We'll pick this paper sometime. And right now, the newer version of that is called Colossus. Okay. Interestingly, most systems at Google need some sort of store which is managed by Colossus. They need network capabilities, which is powered by Jupyter. They need compute and memory, which is powered by Borg. This is inspired Kubernetes. And they need some config setup, which is taken care of by Spanner. So amongst these four, Jupyter is used by Dremel for network capabilities, and storage is also used. And these shards that you see are definitely coming from Borg. So when you're making a query, the query manager estimates how much compute do you need. The compute is measured as the number of machines into the number of threads that they have. So the total number of threads defines the compute power for this query. If you need more compute power, you can increase this. If you want to reduce the compute power for this query, you can do that. Based on that, the time taken by the query will increase or decrease. Now, when the result is fetched from disk or distributed file store, it is propagated upwards to the parent shard. And then it is propagated upwards to the parent shard. You see, I've added dots over here very sneakily. That means that there can be any number of levels. And the query manager is something which suggests how many shards will be needed to effectively aggregate this kind of a query. What's happening at a high level, if you've worked with segment trees or interval trees, is we are taking results, we are aggregating them, putting them on the higher shard, and we are going up the tree till we reach the root. This architecture you'll see repeated at Google many times. A tree architectures, I think they like it because they also have it in Google Monarch. It's highly efficient because queries are usually answered in tens of seconds, and therefore the clients, the users, can make decisions quickly. They don't need to go to lunch now for every query to complete. Instead, they can sit on their desktop, wait for a minute, maybe the loading goes on, and then they get a result, and then they fire a new query based on that insight. The system is also smart in the sense that it has a prefetch cache which fetches data relevant to the query that you just made. For example, when you say, tell me the number of people who have visited a restaurant while going on a long drive, it's going to get you data around long drives, and it's going to get you data around restaurants prefetched in cache. So the rest of the queries, the upcoming queries, are most likely going to fetch the same kind of data. It has a 95% hit rate. So you don't have to go all the way down to the leaf. You don't have to fetch from local disk, and worst case, you don't have to fetch from distributed file store. You can get it from a cache with a 95% hit rate, which really improves the latency. Another optimization that is very useful is when product managers don't want perfect answers. They're okay with getting 99% accuracy or 90% accuracy. For example, you want to know the percentage of people who in a long trip have gone to a restaurant. You don't have to get 56% dot. You can be off by plus minus 2%. It's not going to affect you. But why is that important? If you have this luxury, if you can make an approximate result, then the query manager tells the root that when you have 98% or 90% of the results, give me a response. Don't keep the client waiting. So it's possible that L3 is down or L4 is taking a long time. We don't need to wait on all the leaf nodes. We can give a response the moment we are sure enough. This opens up a lot of possibilities. If you want to see the top K results, so what were the top 10 most popular YouTube videos, you don't need to go through the entire YouTube video set. You can go through maybe 98%, 95%, and those last 2%, the tail latency is very high. So if you ignore them, then you really save on latency. And the final optimization that Dremel brings is columnar storage. All data processed by Dremel is stored as columns. The benefit of this is columnar compression is much better, especially when you're looking at aggregate statistics. For example, if I have tuples like this, where the name, country, and age of a person is to be noted, so this would be row 1. The way I would store this would be, next to this, I would attach row 2, name, country, and age. Row 3 then would come here with name, country, and age. If I wanted to know the average age of my users, I would need to scan all of this data. I would need to sequentially read all the data. Instead, if I could keep all the columns together, age 1, age 2, age 3, name 1, name 2, name 3, and country 1, country 2, country 3, then the average age would just require a scan of 3 data points instead of 9 data points. So faster scans would be possible because of columnar storage. The other thing which is really important is compression. If you have the same kind of data being stored together, then you can use compression algorithms like non-zero run length encoding to reduce the space consumed by your data. This means you need lesser storage, lesser bandwidth, so the processing is usually faster. But non-zero run length encoding has some issues. One of the things is whenever you have a block of zeros and you want to query between that block, it's difficult to find a head when all the records are zeros. To actually hydrate this data, you have to go up to the top header. To avoid this, Google came up with its own compression algorithm, which has inspired many other systems. Apache Parquet, for example, has picked up ideas here. The engineers at Twitter developed this format. Now it's open source and it's got even better algorithms than this. But the basic idea here, if you know about Huffman encoding, is you take your data, you spread it out like a tree. So a trip has an ID, a trip has multiple locations in it. It has multiple users, 0 to star. Each of those users may have multiple interests. They have a country defined or they don't have a country defined. The interest may have a type. So I'm interested in burgers, I'm interested in pizza, and a location may actually be a polygon. So that enclosed space, and you also have a type of location. So it may be a restaurant, it may be a playground, whatever. What Google did is take each of these data fields and compress them in a way that it is easy to decompress later. When you're querying for that data, it's going to be easy to find the range that you're looking for and get the aggregate statistic. The algorithm for converting these objects into a format which is suitable for columnar storage is very involved. I went through hours of resources and decided not to put it here. If you're interested, I have the links in the description. And if you want to know, is it going to be useful to me as an engineer? Well, no. But if you want to play around with the math, go ahead. Huffman encoding algorithm for choosing a path in a tree have some similarities to the Dremel algorithm. So that's it for Google Dremel. It's a short, concise paper. It's just 8 pages long. That's why the main core ideas were explained so quickly. If you have any doubts or suggestions, you can let me know in the comments below. I'm trying to create a system design judge at my startup called Interview Ready. Do check it out, and I'll see you next time. Bye-bye.